So you don't need to, as long as you start to register, that's fine. Later than going around. Just so register. Yeah. Guys, do question one, please. I'll give you a few minutes and see if they do it. Anyone hasn't signed me? Hello, guys. You all sign? You all sign? You all sign? Can you guys over here see that screen? You can? Sure. Let me show you. If you haven't done question 1, I know many of you have already done question 1, but let me show you how to do question 1 if you haven't done it. So you have a normal variable with mean, mu, and variance sigma squared. You want to find the MGF. Since the normal distribution is a continuous distribution, we use the continuous definition of an MGF, which is this guy here multiplied by the PDF. All right, remember, this is the continuous definition of an MGF, right? This multiplied by the PDF. This is the PDF of a normal random variable. Now this is a constant. You can pull it outside the integral sign. So what you're left with is E of Tx Yes. Now next, I'm going to take 2 sigma squared as a common factor. So you should take 2 sigma squared as a common factor. Then over here you get 2 sigma squared Tx, and here you have x minus mu squared dx. Yes? Right. The next thing I'm going to do is I'm going to take this negative sign outside. So you get this. Because I'm taking a negative sign, I need to multiply this by Tx plus, I'm going to expand x minus mu squared by opening the bracket. So you get x squared minus 2 mu x plus mu squared. You see what I've done. I've taken a negative sign, and so this, you have a minus in front, and this minus become plus, and if you open the brackets, it becomes, you get these 3 terms. Okay. Now I'm going to combine these two. You see there are 2 terms here that involve x, this term and this term. So I'm going to combine the 2, this one and this term. So you get x squared minus 2x okay. So you see what I've done. I have combined these 2 terms to give you this term, right? Now the next step is a crucial one. This may be familiar to many of you, perhaps all of you. I'm gonna because what you have here is a quadratic polynomial, x squared, a term with an x squared in it, a term with an x in it, and a constant term. Now what you can do is you can write this You see what I've done? What have I done from going from this line to this line? What I have done is known as completion of, I'm sure you heard this term before, right? Completion of squares. You have, right? So what I've done precisely to go from this line to this line, I have completed the squares with respect to x. Okay? Right. Now, I'm going to do this. Yeah, you see what I've done? The last two terms over here, this term and this term, do not depend on x. There's no x in this term. There's no x in this term, right? Therefore, these two terms can be regarded as constant, right? And therefore, you can pull them outside the integral sign. And that's what I have done over here. I have pulled this term outside the integral sign, because there's no x in it, right? Now, let's focus on this one, guys. What can you say about this? Yes? What can you say about this? This is equal to 1. Why? Why do you think this is equal to 1? Because the because you see, what you have here inside the square brackets, what you have is the PDF of a normal distribution with parameters, with the mean parameter equal to mu plus sigma square t, and the variance equal to sigma square. And you know from your probability 1 that any PDF, by definition, any PDF must integrate to 1, right? And therefore, the thing inside the brackets must be equal to 1. Yeah, is that clear, guys? Okay. So the answer to this question is equal to this. Since this is 1, the answer must be this. And if you simplify this, after a while, you will get this answer here, which is E. I'm not going to simplify it. I'm sure you can do it. So if you simplify this term here, you will get to this, right? And that's the answer to question 1. Is that clear to you? Any doubts? Feel free to ask me. I will put this online so you don't need to. I mean, as always, I will always put this online so you can see what I have written. Okay. Yeah. Any questions, guys? Is that clear to all of you? All right. Can you do question 2, please, then? You get something with that? Yeah. Okay. If you can't see it, I'll put it over here. Maybe this is better. I should. I'll put it over here if you can't see it that side. Maybe it's better this way. Don't know. All right, guys, can you do a question? I'll give you a few minutes and see if you can do it by yourself. Question 2. All of you guys, you have copies of this? The advance? All right, guys. Let's see how we can do question 2. So you have
Is it possible to put it on both screens?
huh?
Is it possible to put it on both screens? It's just a trick.
Yeah, I know. I don't know how to do it though.
Alright, sorry. Don't worry.
Because you guys can see, like, can you see what I write over there, sir? You can't see? I mean, hello.
That's what I can say.
You can see it, right? Okay, I'm just asking, because sometimes it's like some people may want to look what I've done in the previous page, so that's why I put it here. I put this page over here, and anyways, all right. So this is what we want to show. We want to show that this ax1 plus bx2 plus c has a normal distribution with these parameters. Okay. Now to do questions like this, whenever you are asked to show that something, a function of a random variable or a function of a random variables has a certain distribution, there are many different approaches, but one approach that I will commonly use during this course is the following. Right? Just start with the left-hand side. This is the left-hand side, and call it, because it's a long expression, right? Call it some other name. Say, let's call it y. You don't need to call it y. You can call it whatever you like. Okay. And the first step is to find. The first step is to find the MGF, the moment generating function of y, right? So that will be this. That would be this, okay? Yeah. Now this you can write as yes. Now using, we are told that x1 and x2 are independent random variables, right? Okay, so using independence, you can write this as yeah. Now what you have here is simply the MGF of x1 at TA, and what you have here is the MGF of x2 at TB and multiplied by ETC. Now we know from question 1 that a normal, this is the MGF of a normal variable with parameters mu and sigma, right? So this guy here will be, according to, by this formula, this will be mu1 Ta plus sigma 1 squared T squared A squared divided by 2, and this guy will be mu2 Tb plus sigma 2 squared T squared B squared divided by 2, times Tc. Are you guys with me or not? Yeah, I'm just using this formula here that I just proved in question 1. Okay. Now, what you have here is a product of 3 e terms, or exponential terms. Now, that's the same as 1 e term, with the power being the sum of the powers. So it will be okay. All right, now let's look at this one a little bit closer. So this is what we have got. Now, if you compare, just take a minute and see how this compares to this expression here. I mean, what's the difference? What's the similarity between this expression and the expression over here? The similarity is that in place of mu, you have this expression, and in place of sigma squared, you have this expression, right? So what you have here is the MGF of a normal variable with mu replaced by this, and sigma squared replaced by okay. Do you follow my reasoning? Because what you have here is precisely is of the same form as this, with mu replaced by this expression, sigma squared replaced by this expression, and therefore this whole thing must be the MGF of this, right? And hence y must follow the normal distribution with these parameters. Okay. Is that clear, guys, or not? So, any questions on this? All right. I'll put this online later on. I'll put this over here. Maybe you can see better over here. Can you? Okay. You guys okay? Any questions? expectations, you're just showing that the expectations are equal, and that's not enough to prove that they have the same distribution. Okay, you must always use this approach here, using the MGFs. It's not enough. It's not enough to show that the expectations are equal. Okay. You can't. This approach is not correct because you are just showing that the expectations are equal and then the variances are equal. That's not enough. That doesn't prove. That doesn't prove that AX1 plus BX2 has a normal distribution. To prove this, you must show that the MGF of this is the same as the MGF of this. Right? No. You're just showing that expectations are equal for both sides, the left and right. And the same thing with the variance, but that doesn't prove anything. That doesn't prove that this has the normal distribution. Yeah. The question here is to show that this has the normal distribution. So you should use the MGF approach, not the expectations of the variance. Yes. You guys okay? You guys okay? Okay, you got question 3, guys. Right. Shh. Would you listen, please? So I know many of you have done this, but let me show you. If you haven't done this, let me show you how to do. All right. This is very similar to question 2. So you use the same approach, right? So you start with the left-hand side, which is x bar. So you find the MGF of x bar, which is, by definition, is the expectation of, it's by definition. And this you can write as this, because remember x bar is the average, is the sample mean. Now this you can write as this, right? Now by independence, by independence you can write this as the product of the expectations, right? So this will be, like this, okay? Now, what you have here is simply the MGF of x1 at t by n, and what you have here is the MGF of xn at t by n, right? Now, because x1 to xn are IID, meaning identical and independent, using the identical assumption, each of these is the same thing, right? In other words, you can write this as this, because what you're doing here is you're taking the product of the same thing n times, right? So this is equal to this, right? Now, if you go back to question 1, this is the answer to question 1, right? Now we know this is the MGF of a normal variable. So the MGF of x1, which is a normal variable, is E over n. Are you guys with me? Okay. Now, when you take the nth power of a E term, what do? What happens is that you're taking basically n becomes, you're basically multiplying everything by n, right? You're multiplying the power inside by n. That's what you're doing, all right? So what you have here is mu t plus sigma squared divided by n times t squared divided by 2. Okay. Now, if you look closely at this, guys, and compare this expression here with this expression, you see the similarity. The difference between this one and this one is that in place of sigma squared over here, you have sigma squared by n. Hence, this must be the MGF of a normal variable with parameters mu and variance sigma squared by n. Can you see what I'm doing? Because what you have here is the same as this, with sigma squared replaced by sigma squared by n. Hence, we have shown that x bar follows this distribution. All right? Is that clear, guys? Yeah? Can you do question 4, guys, please? Question 4, please. let me put this over here. Hopefully you can see better. Better over here. Question 4 is pretty trivial. I mean, it shouldn't take you a few minutes to do, a few seconds to do this. All right, question 4 is, when I use the word U and I, it always refers to the continuous uniform distribution, not the discrete one, right? So in this case, the PDF, if you look at the notes, you will see the density function is this is the density function of the continuous uniform. Yeah? Oh. Okay. And so the MGF by definition is the integral from a to b of etx times 1 over b minus a dx. Take this outside the integral sign, you get okay, take the limits from a to b and you get the answer that etb divided by t minus eta divided by t, and this is the answer to question 4, I believe. I mean, so it's really pretty straightforward. Okay, you shouldn't have difficulties doing this question. Okay. And let me put this over here. Question 5 is also straightforward, not really difficult. X has this notation here will always refer to, this notation refers to the continuous exponential distribution, which has, if you look at the lecture notes, this is the density function. This is the density function for the exponential distribution, right? So the MGF is by definition, this is the MGF. Lambda is a constant, so you can pull it outside. So it becomes lambda times the integral of e of minus this. Okay. Now the integral of this is not difficult. You have minus lambda minus t. Take the limits from 0 to infinity. Okay. At infinity, if you assume that lambda is greater than t, the limit will be 0. And at 0, the limit will be, right, provided if lambda is greater than t, right? Because otherwise the integral will diverge, will not exist, right? So this condition is important. Okay. So if you simplify this, you get lambda minus t, which is the answer. Okay. So that's question 5. Can we try question 6, guys, now? everybody sign the attendance sheet, guys. Okay, guys. What are the required is x less than is it x? This is small x, yeah. So f x less than equal to x implies that log of x must be less than equal to log of x, right? Now, because of the property, this property here, and log of x must have a normal distribution. Yeah. So log of x has a normal distribution. Yes, because of this property. So because of that, this must be equal to this. Remember I told you, if you look in over here, right? This is the CDF of normal distribution, phi and x minus b whatever is equal. This is CDF of normal distribution. And over here, log of x has the normal distribution, parameters mu and sigma. And therefore, by this equation, this is it 47 or 70? Yes. By this equation number, this must be equal to this. Okay. Are you guys okay? Let me try question 6 by yourself, and when you guys come next week, I will show you how to do it. I will show you in the lectures how to do question 6. Okay? That's on Tuesday. Yeah? Okay? Yeah.
Igual from the